I welcome you all again to the second lecture of the course Econometric Methods. Myself, Dr. Muhammad Imdadul Haq, will be with you for this lecture. We come to the method of least squares. The relationship between consumption and income, it can be divided into systematic and non-systematic errors. We assume, say, C is equal to alpha plus beta x as systematic as other things are assumed constant. We consider it an exact and deterministic relationship. Theoretically, it is plausible, but in actual practice, other variables also affect consumption. That is, C is equal to alpha plus beta x plus u, where u captures the influence of other variables, that is non-systematic. From this non-systematic relationship, we have to find the systematic relationship part. So the idea is to fit a line which will be the best representative of the data. We have a picture in front over here. Now we see that there are three data points. There are three points are designated over there, and we fit a line. We have fit a line in such a way that that line is having one data point as a positive deviation, it is denoted by +2, and two data points which are having a negative deviation of -1 and -1. The difference between the actual points and the line is what we call error. The line will be taken as the best fit. But error is inevitable. We only want to minimize this error. The line should be fitted in such a way that the error would be 0 or minimum. Using this criterion, we can fit another line having 0, but we can fit another line having 0 error, but there can be several lines showing the same relationship. So the problem of these errors arise because of the sign. Let us take another line. This is showing that there are 3 data points. Now the line is passing exactly through 2 data points, and the other one is having a deviation of +3. So when this line is fitted, we can further minimize this. In this case, if the line is passing through the 2 lower points, the error will be further minimized. But the first line is better because it gives due weightage to all the points. This is assumed to be better because it gives due emphasis to all the data points. Another criteria is that we square the errors and minimize the sum of the squared errors. Like say, we have line 1, the errors are 2, -1, -1. So if we square it, so this 2, it becomes 4, -1, square it becomes 1, -1, the square becomes 1. So when we sum it, it is 4 plus 1 plus 1, that is equal to 6. The second line, the first error term was 3, the division of +3, and the other, there were no errors as the line was passing through these points. So now when we square 3, we get 9, and for 0 we get square is 0, for others square is 0. When we sum it, it is 9. So for the first line, the squared error term was 6, and for the second line, which was passing through 2 of the data points, the squared error is equal to 9. Now we should be preferring the first line over here. So this is what is called as the least squares method. When we use the least square method, we get the best line using the first criteria. So it is evident that least square method is a better criteria for fitting the regression line. Now we move to the concept of population regression function. Let us consider a hypothetical country with say 27 families. These families are divided into 50 groups. Now let us take their monthly income. This is monthly income and we have 5 values of monthly income. 90, monthly income 100, monthly income 110, monthly income 120 and monthly income 130. So there are 5 fixed values of monthly income X, and each value of the income has several corresponding values of consumption. Like the income of the family which is having an income of 90, one is having a consumption of 50, other is having a consumption of 55, the next one is having a consumption of 60, then 65, 72 and 76. Similarly, the family having a monthly income of 100 is having a consumption of 60, the next family is having a consumption of 65, next one is having a consumption of 70, next one is having a consumption of 80, finally 85, and likewise it is happening for all the remaining 3 levels of income. Now, if we simply go by calculate the mean of this, that is, we add this all these consumptions expenditures, the monthly consumption expenditure 50 plus 55 plus 60 plus 65 plus 72 plus 76 plus 60, 65, 70, 80, 85 plus 75, 85, 90, 95, 100 plus 75, 90, 100 plus 105, 110, 120, then again plus 100 plus 110 plus 115 plus 120 plus 120. So for if this we add all this consumption expenditure and divided by, there are 27 families, so we divide by 27, it turns out to be 2358 divided by 27, that is equal to 87.34. This is what we refer to as unconditional mean. It is unconditional as here we have not considered the different income levels of the different families. Now, the probability of consumption for the first group is 1 by 6. This is conditional probability, which means probability with certain restrictions. Here the condition probability of y given x when x is equal to 90 is 1 by 6, because we are having 1, 2, 3, 4, 5 and 6 families. Similarly, for the next one, for the second group, probability that probability of y given x when x is equal to 100 is equal to 1 upon 5, as there are 1, 2, 3, 4 and 5 families. And so for the third group, the probability of y given x when x is equal to 1 by 20 is equal to 1 by 5. Next, for the fourth group, say the fourth group, they are again 1, 2, 3, 4, 5 and 6. So we have the probability of the fourth for the fourth group, probability of y given x when x is equal to 130 is equal to 1 by 6, and for the third group and for the last group it is again 1 by 5. Now what we do, we multiply the consumption expenditure with the respective probabilities. Like it is 1 by 6 for the first, all it is there are 6 families, so we have 1 by 6, we multiply it with the consumption expenditure, that is the consumption expenditure what we have assumed over here. So what we simply do over here is we multiply 1 by 6 with 50, then second time multiply 1 by 6 with 55, then 1 by 6 with 60, then 1 by 6 with 65, then 1 by 6 with 72, then 1 by 6 with 76. Next time there is 60, 65 for the next family in monthly income group 100, it is 60, 65, 70, 80, 85. So we do the We multiply this. There are 5 families, so we have that 1 by 5 multiplied by 60, 1 by 5 multiplied by 65. So this process, it continues for all the 27 families. Now once we have done the calculation, we get the values like this: 8.33 for the first one, then we have 9.16, then 10, then 10.83, then 11.66, then 12.66. Similarly, for the family which was having a monthly income of 100, this was, we have done 1 by 5 multiplied by 60, so we get this 12. Next time what we have is 1 by 5 multiplied by 65, so we get 13. Then we do 1 by 5 multiplied by 70, we get 14, and likewise we continue. We do this for all the 5 different income levels. Now we add all this. So when we add for the first monthly income group, we get, for the monthly income of 90, we get the value, average value of 63. For the monthly income group 100, we get the average value 72. For the monthly income group 110, we get 89. For the monthly income group 120, we get the average as 100. And for the monthly income group 130, we get the average as 115. Now, only one level of consumption can be associated with the level of income, which gives the relationship between consumption and income. The probabilities are all given over here. So, instead we say that each one of the consumption level is associated with the level of income. We calculate simple average. If all the consumption level has, if all the consumption level has probability 1, that is a different thing. We calculate simple average, but here we have probabilities which are less than 1, that is 1 by 5 and 1 by 6. So we find the conditional mean. It will be the average of, also we call it as the expected value. Now expected value of y given x when x is equal to 90, we add all these 8.33 plus 9.16 plus 10 and 10.83 plus 11.66 plus 12.66, so we get 63. Similarly, the expected value of y given x when x is equal to 100, we have done the calculation over here, we get 72. The expected value of y given x when x is equal to 110, that is x is equal to 110, we have added all these values, we got the number 89. Similarly, when x is equal to expected value of y given x when x is equal to 120, it is equal to 100. And finally, the expected value of y given x when x is equal to 130 is equal to 115. Now, what is the expected value of monthly consumption expenditure of a household? If I simply this question, I repeat the question. What is the expected value of monthly consumption expenditure of a household? You remember we have done we calculated all these, we add all these numbers from 50, 55, 60, 65, 70, 76, then 60, 65, we up till 130, we add and divide it by the total number of families, which is here is 27. We have earlier got the answer 87.34. That is the unconditional mean. Now the next question. What is the expected value of monthly consumption expenditure of a family whose monthly income is 90? It is 63. Similarly, say, what is the expected value of monthly consumption expenditure of a family whose monthly income is 120? The answer would be 100. So, the population regression function is nothing but the locus of the conditional means of the dependent variable for the fixed values of the independent variables. This we will be having a look at this picture, and it will be explaining what is this population regression function. I repeat, the definition of population regression function is nothing but the locus of the conditional means of the dependent variable for fixed values of the independent variable. From this picture, it is evident for each monthly income 90, 100, 110, 120, 130. For each monthly income X, there are many values of monthly consumption expenditure that is spread around the conditional mean values of Y. That is spread around. This line I am referring to, it shows the relationship between average of the dependent values of C and the given values of the independent variable X. It is achieved by associating average consumption with the level of income. This is what we called as the population regression function. So, to summarize, population regression function shows the relationship between the values of the dependent variable and the given values of the independent variable. Now we can say that the expenditure of an individual family given its income level can be expressed as the sum of two components. Expected value, the first one is expected value of Y given X, which is simply the mean consumption expenditure of all the families with the same level of income. This component is the systematic or the deterministic component. The systematic component or the deterministic component. So this was the first thing. Now the second thing is U. U, which is the random or non-systematic component. So we shall examine shortly the nature of the stochastic disturbance term, but for the moment we assume that it is the surrogate or proxy of all the omitted or neglected variables that may affect Y but are not or maybe cannot be included in the regression model. Now we take one of the income group. We have just taken we have just taken the income group 90 and we have the data for the consumption for this monthly income. What was the consumption? Monthly consumption expenditure 50, 55, 60, 65, 72 and 76, and if we recall the conditional mean value was 63. We are calculating the error. We are just doing it for the only one as a sample, the monthly income 90 group. So the first value of U1 is 50 minus 63, that is equal to minus 13. For the second one, it is for the second error term is equal to 55 minus 63, that is equal to minus 8. The third one is 60 minus 63, that is minus 3. Next is 65 minus 63, that is equal to 2. The next one is 72 minus 63, that is equal to 9. And the final one is 76 minus 63, that is equal to 13. Now, this U is the difference between the individual values of consumption and conditional values of consumption. To explain the concept of U, let us take the case of the first household, which we are taking over here. Now, average values of U, that is, if we add all this, minus 13 plus minus 8 plus minus 3 plus 2 plus 9 plus 13, if we add all this, the negative values will cancel the positive values and the result will be 0. So, we have a functional relationship between consumption and income by pre-assuming that other variables are acting in such a way so that they are utilizing the values of other. So the net impact of the values is 0. If influence is 0, the population regression function shows true relationship between consumption and income. So we fit the regression line in such a way that the net impact will be zero. The stochastic specification has the advantage that it clearly shows that there are other variables besides income that affect the consumption expenditure, and that an individual family's consumption expenditure cannot be fully explained by the variables included in the regression model. Now we move on to sample regression function. The same income group and the same we have the same data over here, that is we have the consumption, the monthly income of 90, monthly income of 100 and the associated things. But see, at most of the time what we have is only a few sample y corresponding to some values of fixed x. So we have to estimate the population regression function based on the sample we have. So the entire population is divided into 5 groups, and now from each group we are going to select one household. So now we have highlighted them by yellow color. Say for x, when x is 90, the selected sample is 65. When x is 100, for the 100 monthly income group, the selected sample is 80. For 110 income group, the selected sample is 90. For 120 income group, the selected sample is 100. And for the income group of 130, the selected sample is 110. Now we have only one value of y corresponding to the given x. These are the samples selected, and we assume that the sample has been selected randomly. So it can be seen from the points that some points are not on the line as it is shown in the scatter diagram, but these points, what we have drawn the line, that is, this line is called as the sample regression function. The line which is being shown over here is sample regression function. Now here we are denoting it, we are representing it by y hat. Y hat is equal to alpha hat plus beta hat x. When in population regression function, this y hat was not there. Y was equal to alpha plus beta x. But when we are estimating, we denote it by letter hat, hat onto the letters. That y hat is equal to alpha hat plus beta hat x. From this SRF, or from this sample regression function, we will estimate the population regression function. Now, alpha hat is an estimator of alpha, beta hat is an estimator of beta, y hat is an estimator of expected value of y given x. So, the sample statistics is the method to estimate the population parameter using the sample. Now, what are the sample statistics? Alpha hat and beta hat. They will be used to measure alpha and beta. Now, as all the values do not fall on the regression line, only it means we have the y is equal to y hat plus e, the error. So if we define error, error is equal to y minus y hat, where y is the actual value and y hat is the estimated value, and this e, that is the difference between the actual value and the estimated value, is known as the sample error, and it is used to estimate the value of u from the population regression function. But now the question is whether can we forecast the monthly consumption expenditure in the population as a whole corresponding to x that is selected, or simply we can estimate this population regression function from the sample regression function. There may be issues because of a selection of sample. Now, I select another sample. Again, for 90, the sample selected is 60. That is the earlier in the first case when we selected the sample, those are highlighted by the yellow color, but now the selection of samples is being highlighted by, say, green color. So for 90 it is 60, for monthly income 100 it is 70. Now for monthly income 110 it is 90. So 90 it was there earlier also in the earlier sample, selected sample, and here also it is there. And for the monthly income 120, the consumption expenditure is 110, and for the monthly income 130, the consumption expenditure is 120. So now we have two samples selected. Now, so we can now have two sample regression functions. The question is, which among these two sample regression functions represent the true population regression function? This question becomes more complicated when we have many sample regression functions. And we can have as many sample regression functions as many samples there are. Now we have two sample regression function to represent the same regression line as is shown in this figure. So the main purpose of regression analysis is to estimate the population regression function using the sample regression function. Now, to any point, there is a point A. So what happens, and there is a, here it was denoting xi. So if we take this xi, so yi over here overestimates the true expected value of E upon x. So what is expected value of y given x? Now in this case, in terms of xi, now there is this, our sample regression function is overestimating. And let us take a point to the left of A. So the left of A, your population regression function is more than the sample regression functions. So in this case, what is happening? To the left of point A, what we are having, that the sample regression function is underestimating the population regression function. And over here, to the right hand side of A, the sample regression function is overestimating the relationship. So the main purpose here is that, say, assuming that the sample regression function is a true representative of the population regression function. In that case, what would be the process which will make the SRF the best representative of the PRF? That is, which will make the sample regression function the best representation of the population regression function. That is the closest one. In other words, you can say that how to make alpha hat as close as possible to the population alpha and beta hat as close as possible to the population beta or the true beta, even if the values of true beta and true alpha are unknown. So the work of regression over here is to estimate the sample regression function which is the best representative or which is the closest to the true population regression function.